Module 5, Part 2 is about special factoring and a general approach to factoring. So we're going to need all the factoring skills, like how to factor trinomial, how to factor by grouping, how to factor by pulling out the greatest common factor that we saw in Part 1 in this section as well, and a couple more skills that we're going to start the video with. So please make sure you're completing your guided notes as we go along. So as a quick warm-up, so we haven't forgotten everything we covered in the last video, let's do some examples. So for this first example, I've got 5x squared y squared minus 15xy cubed. And I have two terms here, so I'm going to go ahead and pull out the greatest common factor. I know it's going to have a 5 because 5 and 15 have a greatest common factor of 5. I've got an x squared and an x, so I'm going to pull out an x. We always pull out the lowest degree. I've got a y squared and y cubed, so that's going to be y squared. And I think to myself, okay, what do I multiply 5xy squared by to get 5x squared y squared? Well, that's just going to be an x minus, what do I multiply 5 by to make it look like negative 15? How about a negative 3? I've already got an x. I've got y squared. I need one more y. So that's factoring by pulling out the greatest common factor. In the second example, 3x squared plus 22x minus 16, we're going to have to find the factors of AC that add up to B. So let's go ahead and get started by labeling our ABCs. So A is 3, B is 22, C is negative 16. So A times C is 3 times negative 16, that's negative 48. And I got to say, okay, what are some factors of negative 48? That add up to 22. Well, how about negative 2 times 24? So I have 3x squared minus 2x plus 24x minus 16, and then I factor by grouping. The greatest common factor of 3x squared and 2x is just going to be an x. The greatest common factor of 24x and negative 16, is going to be 8. So plus 8 times 3x minus 2. Remember, we want these two pieces to look the same. I collect the greatest common factors and what they left behind. Now, when we're finding the factors of AC that add to B, when we've got a leading coefficient of when A isn't 1, we have to go through this factoring by grouping method. But we don't necessarily have to do that when A is 1. So for this next example, A is 1, B is 3, C is negative 10. And I'm trying to find the factors of negative 10 that add to a positive 3. Well, how about 5 times negative 2? And I could go ahead and rewrite this as x squared minus 2x plus 5x minus 10. And I could factor by grouping. And we'd see that my factors are a positive 5. Oh, interesting, interesting. And a negative 2. Oh, very interesting. Very, very interesting. That doesn't work in this first example because A doesn't equal 1. So when A is 1, we can use this shortcut, which I believe I mentioned briefly in the previous video. Our last example, we've got x cubed minus 7x squared plus 7x minus 49. We got to factor by grouping. In our first group, the greatest common factor is x squared times x minus 7. In our second grouping, the greatest common factor is a positive 7. I collect the greatest common factors and what they left behind. And if I ever wanted to check my answer, I could check my answers after I factor, as I could multiply. So we're going to multiply to check our answers. So now we've had a nice little warm-up, a little reminder of how to factor, especially how to factor trinomials when A is 1 or when A is not 1. Let's take a look at the next slide. So what I'm trying to see is, can you guys find a pattern for all of these examples? Stop a second and think about if you see any patterns. Because what you might notice is that, okay, I've got 9 and 6. Well, 9 is 3 squared, and 6 is 2 times 3. I've got 9 again, and 6 is negative 2 times 3. Same thing here, I've got 4 squared, and this is 2 times 4. Got 5 squared, and this is 2 times 5, right? These first ones, these are going to factor. If I find the factors of AC that add up to B, this first one factors into S plus 3 times X plus 3. My second one, the sign changes, but still X minus 3 times X minus 3. I could rewrite this as a perfect square. Same thing is true for this next example. I've got X plus 4 squared, X plus 5 squared. What do we think is going to happen here? Here's 5, but this isn't 2 times 5. It looks like it's 2 times 2 times 5, and this is 2 squared. So this is going to factor to 2x plus 5 squared if we went to all the trouble to factor by grouping. This is the product of perfect squares. And the product of perfect squares are always going to factor like this. If I have a first term that's a perfect square and a last term that's a perfect square, if my middle term is 2 times the square root of my first term and the square root of my second term, then it's going to factor into a perfect square. Do you need to memorize this? No, do not memorize. You could just find the factors of AC that add up to B. That's what I would recommend you do. But this can be a handy-dandy tool as you're going through and solving, especially problems like if I've got x squared minus 12x plus 36. Well, what are the factors of AC that add up to negative 12? AC is 36, negative 6, and negative 6, right? And that's really nice to have it be x minus 6 squared. But these next two examples are a little bit bigger. They're a little bit heftier, right? 144, that's 12 squared. So this whole thing is 12x squared. 25 is 5 squared. Is my middle 2 times 5 times 12x? Yeah. So this is going to factor to 12x. How do we turn the page? Here we go. This example right here is going to factor to 12x minus 5 squared. This next example, I've got an x and a y. I've got 2x squared, 7y squared, and this middle term is 2 times 2 times 7 times y. No, it's not. This isn't going to factor like this, right? Because 2 times 2 times 7 times y, that'd be 28xy. So this one isn't going to factor. Right? These methods still work. Some people call this a shortcut. I don't like it. I don't want to memorize it. I want you to find the factors of AC that add up to B. That's the most important part. Let's take a look at another pattern. We've seen these before. This is a difference of perfect squares, and we might have seen that these factor into the product of a sum and a difference. Sum meaning add, difference meaning subtract. So x squared minus 4 becomes x plus 2x minus 2. X squared minus 25 becomes x plus 5x minus 5. And that's the same is true for all of these because our middle term is 0. And it doesn't matter if I put the sum or the difference first, but typically we say it's the product of a sum and a difference. So typically I put the sum first. What about more complicated ones like this, when a isn't 1? What do we think that pattern might be? How about 2x minus 3 and 2x plus 3? For our last one, how about 3x minus 1? Remember, 1 is a perfect square. And 3x plus 1. These are all the product of a sum and a difference. All that changes is the middle sign from negative to positive or positive to negative. And because of that, my middle terms, my b terms, will cancel out. So if I have a difference of two perfect squares, now note they have to be perfect squares. I can't have like x squared minus 7. Those aren't perfect squares. I can't have 4x squared minus 5. 5's not a perfect square, even though 4x is. They both have to be perfect squares, and then they're going to factor into the product of a sum and a difference. So for example 1, I get x plus 6, x minus 6. Example 2, I know I'm going to have an 8 because 64 is 8. The square root of 64 is 8. But 4a squared, that's going to be a 2a. For problem 3, I've got 4x minus 7y, 4x plus 7y. And for problem 4, think of this first term. It is a perfect square. I could rewrite it as x squared squared minus 81. This is going to factor into x squared plus 9, x squared minus 9. Well, x squared minus 9, this is also a difference of squares, so we're going to have to keep factoring. I've got x squared plus 9 times x minus 3 times x plus 3. Now, how did I know to keep factoring other than the fact that I'm a math professor? Well, I knew to keep factoring because this is also a difference of squares, and it's going to be one of our steps when we look at a general approach to factoring, which is what we're going to talk about next, after we talk about finding the sum and difference of two cubes. So this one you will have to memorize. This one you will have to memorize for checkpoints, for exams, for quizzes, right? This you have to memorize. So if I have the product of two perfect cubes, it's going to factor into a plus b times a squared minus ab plus b squared. If I have a difference of two cubes, it's going to factor into a minus b, a squared plus ab plus b squared. So what you're going to do when you see an example, like let's say I had x cubed plus 8, I would see that my a is x, and my b is going to be whatever cubes to get 8, which is 2. And then I just substitute in. I'd have, instead of a plus b, I'd have x plus 2. Instead of a squared, I'd have x squared minus ab. A times b is 2x plus b squared, which is 2 squared, which is 4. We're just substituting in. So we want to start by labeling our capital A's and capital B's. So in example 1, my capital A is is x. My capital B is 3. So we're taking the sum. That's going to give me x plus 3 times x squared minus 3x, which is my a times b, plus 9. For problem 2, we're still taking a sum. My a is going to have an x in it, but it's also going to have a 3. And my b is going to be 5. It's good to know the first few perfect cubes. So that's going to be 1, 8, 27, 64. That's 4 cubed. Yes. And 5 cubed is 125. So those are the first few really good ones to know, just off the top of your head. So this is going to factor to 3x plus 5 times 3x squared minus 15x, because it's 3x times 5, plus 25. Well, this 3x squared, that's going to become 9x squared, because we have to distribute that square to both. We learned that in module 4. Last, I have 3x cubed minus 24, and 3 is not a perfect cube, so you might be able to be like, oh, I'm done. Actually, no, we're not, because we could factor out the greatest common factor. Now I see my A is x and my B is 2. And this time I'm taking a difference. So this is going to give me 3, can't forget about that 3 we factored out, times x minus 2 times x squared plus 2x plus 4. So now that we've seen how to factor the sum and difference of two cubes, the difference of perfect squares, the product of a perfect square, we can take a look at our general approach to factoring. So here's our general approach to factoring. There's two ways I'm going to talk about it. One is in steps, the other's in like a decision tree flow chart. There's a couple different ones. One's more detailed than the other, and we'll go through them. So to start by factoring, our first step is always going to be to factor out the greatest common factor. Also, no negative leading coefficients, right? Then we're going to look at the number of terms in the polynomial. If there's two terms, can it be factored as a difference of squares, as a sum of cubes, or as a difference of cubes? If it can, factor it. If there's three terms, find the factors of AC that add up to B. If there's four terms, factor by grouping. Then you have to see if any of your factors can be factored further. So does that one of them have a greatest common factor? Does another one have, is another one become a difference of squares? Can I factor it again? And then we check our answers by multiplying. So here's kind of the list of steps. You could also think of it as a decision tree. So like start out, is there a greatest common factor? Yes, if there is, factor it. If there's not, don't factor it. How many terms are there? If there's two, it's a difference of squares. Sum of cubes or difference of cubes. If there's three terms, factor, guess and check. That, I don't like calling it guess and check. Your instructors in high school might have said that, but this is finding the factors of AC that add up to B. We aren't guessing, we're like finding which factors of AC add up to B. I've always been annoyed by that. If there's four terms, we factor by grouping. Is each of your factors in simplest form? Yes, then you're done. No, then you got to go back up to the top and start all over again. So this is more of a flow chart. Here's kind of a simpler way to think about it. So if there's two terms, it's a sum or difference of cubes. It should have looked like this. So fix that in your notes. It could be a difference of squares. You got to find the factors of AC that have to be. If there's three terms, and if there's four, you factor by grouping. So there's three different ways to think of it, like a list of steps or a flow chart. I have copies of this big flow chart printed and in the tutoring center. I also have one up in our Canvas course if you want to look at it. So let's do so many factoring examples. So the first thing you want to do for all of our examples is check for our greatest common factor and then look at the number of terms to determine our next step. So for problem 1, I look at 9p plus 45. The greatest common factor is 9, so I'm going to pull that out. That leaves me with 9 times p plus 5. And I can't factor any of those any further. P plus 5 is in its smallest terms, and so is our constant. So let's switch to a less angry color. Example 2, I've got 8x squared y squared plus 4xy. I'm going to go ahead and pull out the greatest common factor, which is a 4xy. That leaves me with 2xy plus 1. And I see if I can break anything down further. I have 2xy plus 1. This has two terms, but it's not a sum or difference of cubes. It's not a difference of squares. So this is fully factored. Example 3, believe it or not, this has two terms. The greatest common factor is this a plus b. So I pulled this out. And that leaves me with 5x minus y. So now this one is fully factored, and I don't have to do anything else. Example 4, I have 16x squared minus 9y squared. This is a difference of squares. So I'm going to have 4x minus 3y times 4x plus 3y when it's fully factored. For problem 5 and 6, these are differences of this is a sum and a difference of cubes, so I'm going to have to use that formula. Difference is a minus b times a squared plus ab plus b squared. And for the sum, it's a plus b, and that negative moves to our second space, ab plus b squared. So we start by labeling our a's and our b's. In this case, my a is 2x and my b is 3. So I have 2x minus 3 times 4x squared, because it's 2x squared. You distribute, plus 6x plus 9. This example, I've got 10y as my a, because 10 cubed is 1,000, and b is 1. So I have 10y plus 1 times 10y squared, that's 100y squared, minus 10y plus 1. 7, I can't factor out a greatest common factor. This is a sum of two cubes, of two squares. Sum of two squares is not factorable. And I'll do a simpler example to prove that to you. So if I had x squared plus 4, and I wanted you to factor this, you might say, okay, we'll find the factors of AC that add up to B. Well, are there any factors in this case of 4 that would add up to 0? 2 times 2, negative 2 times negative 2, 1 times 4, negative 1 times 4. No, because this middle term our b is 0, and none of these add up to 0. So this is not going to be able to factor. I've got x squared plus 10x plus 25. So for all of these are all trinomials, all these examples. We're going to find the factors of AC that add up to b. Here a is 1, b is 10, c is 25. What are some factors of 25 that add up to 10? How about 5 and 5? And our a is 1, so I can just rewrite this as x plus 5 times x plus 5, or as x plus 5 squared. For problem 9, again, my a is 1, b is negative 5, c is negative 6. And I say, okay, what are some factors of AC, which is negative 6, that add up to b, which is negative 5? How about negative 6 times 1? My a is 1, so I can write this as y minus 6, y plus 1. This shortcut won't work for problem 10. Here my a is 2, my b is negative 1, my c is negative 6. So AC is going to be 2 times negative 6, which is negative 12. What are some factors of negative 12 that add up to negative 1? I could write out all the factors if I wanted to, but I could also see that 3 times negative 4 is negative 12, and those added together add up to negative 1. So I'm going to have 2x squared minus 4x plus 3x minus 6, and we factor by grouping. The greatest common factor of my first pair is 2x. The greatest common factor of my second pair is 3. I collect my greatest common factors and what they left behind. For these last two examples, I have 4 terms, so I need to factor by grouping. We use our grouping symbols. For my first pair, the greatest common factor is y squared. For my second pair, the greatest common factor is x squared. That leaves me with y squared plus x squared times x minus y. And this is a sum of two squares, so I can't factor this any further. Example 20, we factor by grouping. The greatest common factor of 20x cubed and 4x squared is going to be 4x squared times 5x minus 1. The greatest common factor of negative 45x and negative 9 is a negative 9, 5x plus 1. I collect my greatest common factors and what they left behind. And I see that this is a difference of perfect squares. So this is going to factor to 2x plus 3, 2x minus 3, and we don't forget this 5x plus 1. So our last two examples are about trinomials in form. And what trinomials in form are trinomials that we could rewrite to look like ax squared plus bx plus c. So for the first example, I have x to the fourth minus x squared minus 6. Notice 4 and 2 is 1/2 of 4, and 4 is an even number. So some clues that you're going to be able to do this are when you have even exponents and your b term's exponent is half of your a term's exponent. So I could rewrite this as x squared squared, because that's our power rule when it comes to working with exponents, minus x squared minus 6, right? So let's let u equal x squared. I can substitute u squared minus u minus 6. Now I have something that looks like a trinomial in form. I know that I can find the factors of AC that add up to b, and this is a common example that I've used, right? The factors of -6 that add up to -1 are -3 and 2. So I can write this as u minus 3 times u plus 2. I can use that shortcut because our a term is 1. And then I can factor this like this. I could write this as x squared minus 3 times x squared plus 2. I didn't really need to do the u substitution. So then this next example I won't. I could have just left it as x squared, and we would have been able to solve this as well. So our second example, I've got 6y to the fourth plus 7y squared minus 20. I can write this as 6y squared squared plus 7y squared minus 20. Now I have something that looks like a trinomial in form. I need to find the factors of AC that add up to b. So I need to find the factors of 6 AC, which is 6 times -20, so -120, that add up to 7. So I could think of -12 and 10. That's not going to work. I could think of -20 and 6. That's not going to work. I could think of 4 and -30. That's also not going to work, right? But we're going to have to keep looking. How about 8 and 15? Let's make 8 negative, and then that's going to add up to 7. So I've got 6y squared squared minus 8y squared plus 15y squared minus 20. And then we can factor by grouping, and there's going to be a lot of parentheses involved, right? So these are my two groups, changing colors for clarity. The greatest common factor in my first two terms is going to be a 2y squared. That leaves me with y squared minus 4. My greatest common factor in my second group is going to be a 5, y squared minus 4. These look the same, so I did it right. I've got 2y squared plus 5 times y squared minus 4. I notice that y squared minus 4 is a difference of perfect squares, so I can rewrite that as 2y squared plus 5 times y minus 2 times y plus 2. And then this is going to be fully factored,